I will be talking about a fast and accurate sequence alignment, but actually, the right title for my talk is What is Wrong with the Smith-Waterman Sequence Alignment. In the interest of full disclosure, nothing is wrong. But returning back 30 years ago to a famous paper by Wingron and Waterman, how to choose these parameters, alignment parameters, remains guesswork to both the expert and the novice. A lot of things changed in the last 30 years. We now know a little bit how to select these parameters, even so very small fraction of bioinformaticians actually get into the Baum-Welch algorithm and really select parameters. And in many cases, this procedure is completely inappropriate for the biological task at hand. And I will go a little bit before we start into the art of problem formulation. In my class, I spent a lot of time on how to transform fuzzy and imprecise biological problem into the precise biological problem. For example, this is global alignment precise computational problem. Everybody in this room knows about this. And then I tell my student about this local alignment, which basically just adds 0. And my students are not impressed. They're asking, why? What is the big deal? Why do we spend time on this? I can figure it out in my sleep. And then I tell them a story that when I started working in computational biology, I read my first bioinformatics paper in 1985. By the end of 1986, I have read all bioinformatics papers ever published. But I started going through them in the chronological order. So when I started reading about local alignment, I first read papers by Peter Sellers, a mathematician from Rockefeller. And it was painful. It was very difficult and non-elegant. And then I moved from, it was 1980, and then I moved to 1981, and that's when I read the Smith-Waterman paper. The beauty of the paper is not the algorithm. The beauty is the problem formulation. If you think that this problem formulation is trivial, go back to 1980 and see whether it's trivial from 1980. It was not trivial. It was made so simple and available to undergraduate only after this formulation. So asking the right question is an art. Well, I personally thought that until 2 years ago, I thought that alignment problem is completely solved. My last alignment papers on the duality theorem for sequence alignment and Jaroslav Skriver's characterization of Hilbert basis was written 30 years ago, and I thought I will never return to this topic. But I was wrong. And as it turned out, many people in bioinformatics community, particularly in the telomere-to-telomere community, realized that we were wrong. There are many interesting and biomedically important regions for which we have no clue how to compare them. As a result, we have no clue how to do association with diseases, for example. So 20 years ago, some people in this room were participating in sequencing of the human genome, but of course there were many terra incognita dark segments, many errors, many places that weren't sequenced. And 2 years ago, human genome was finally sequenced with a number of biomedically important regions that never were sequenced before. Why they were never sequenced before? Because there are regions in the genome that are extremely repetitive and thus very difficult to assemble. Why they're repetitive? For important biological reasons that we will discuss later. And now there is a project to sequence hundreds of complete human genome. And when the telomere-to-telomere community faced with analyzing the genomes, that's what they wrote in the first pan-genome paper last year. More work is needed to determine how best to align and represent large repeater rates within plant genome. New methods may need to be developed. Now, higher scoring alignment fails to adequately align these regions. This is clear. It is unclear how to select parameters of alignment. And it is clear that standard alignment with whatever parameter is inadequate for analyzing these regions. So I will try to talk about a different approach to alignment that addresses this issue. What are these regions, this newly discovered region? Well, 6% of the genome is formed by centromeres, which are nested extra long tandem repeats. So there's a repeat, and within this repeat, there are other repeats. Like in this case, centromere on chromosome X consists of roughly 1,500 long repeat of length 2 kb. They're all variable, and each repeat of length 2 kb consists of 12 sub-repeats that are even more variable. It is evolutionary enigma because centromeres have highly conserved function. Why they are so variable? And also, it is clear that centromeres are linked to a variety of diseases in cancer and infertility in particular, but they're basically ignored of study association because it's not clear how to align centromere. Until recently, there were no centromeres. Now there are already quite a number of centromeres. So when we started, no reference and no algorithm to work with centromeres. Interesting thing about centromeres, they do not recombine or hardly ever recombine. Why is it interesting? Why we are interested in non-recombining regions? Like here, at this slide, we can find the most recent common ancestor for every blue and green individuals. But the genetic material of this individual, only a small fraction of genetic material on this individual at the bottom is contributed by this most recent common ancestor. In fact, there are thousands of regions in this common ancestor that were not subjected to recombination, and each of them has its own region, most recent common ancestor, and most recent common ancestor of these regions vary for this region. Some of them are recent, some of them are very new. And when we have non-recombining segment, long non-recombining segment, we can study the evolution, we can even learn something about geography. Like in the case of mitochondria, we can study mitochondrial Eve. In the case of Y non-recombining Y chromosome, we can study Y haplogroups and learn a lot of biology. Now, with 23 centromeres, non-recombining centromere, longer than mitochondria, can we now analyze 23 centromeric Adams and Eve? And since centromeres are some of the most rapidly evolving regions of the genome, can we study recent evolution of the human genome if we learn how to compare centromeres? Centromeres are just one of this newly discovered region. Immunoglobulin loci is another one. Immunoglobulin loci actually was assembled, but until 2022 was assembled in only 2 individuals. But it is one of the most highly variable regions in the human genome, and of course, one of the most biomedically important regions. It's another example of highly repetitive regions. It's basically combination of tandem and segmental duplications, and no algorithms to align properly align immunoglobulin loci, G loci, existed until recently. Even between human was difficult, let alone between human, let's say, and chimpanzee. Why is it difficult? Well, you can try, also non-trivial problem, but you can try to decompose human IgA, immunoglobulin heavy chain locus, into the alphabet of duplication subunit. Each letter here is a segment, let's say, of length 10 kb that is repeated and somehow rearranged. This is human and orangutan. You see how different they are. Usually in human and orangutan, everything like identical. They are different even in every 2 people in this room. And making alignment of this region is very difficult. And it is important, because look what happened. This is one of the segment age of length 24 kb, repeated 1 time in human, 7 times in orangutan. What happened? The expression level of every gene, immunity gene, in unit age is increased by a factor of 7 in orangutan. This is definitely important. It's actually maybe a matter of life and death. Why? Because many immunity genes are responsible for fighting, specialized for fighting certain viruses. For example, there is V gene IgHV69 that is particularly important for fighting flu infection. If you have a wrong version of this gene, with just 1 single amino acid substitution, you will be suffering from flu. And the vaccine from flu won't be working on you. 15% of US population has this mutation in this gene. And if we wanted to, so if all of a sudden we increase expression level of certain genes, immunity genes, it's greatly affect our ability to fight viruses, and of course it affects ability to efficiency of vaccination. So how do we align on this region? And so what is wrong with the standard sequence alignment? Let's take the first 2 completely sequencing centromere on chromosome X. I call them SENX1 and SENX2. And let's innocently run sequence alignment. We will get almost like perfect diagonal line. The only thing that is suspicious in this alignment that we construct with classical alignment techniques, very high divergence, 2%, 20% higher than the divergence between 2 human genomes that we expect. How possibly it can be? And there were various speculations that there is some mechanism that greatly increases mutation rate in centromeres, and yeah, so, but the line is straight, just a lot of mismatches on this line. And this is a different alignment, completely different. It has normal divergence rate between 0.1% as in the rest of the human genome, but it has a huge number of tandem duplication and tandem deletions. Okay? Now, interesting thing, these alignment passes do not share any matches. So everything, if second pass is correct, then the first part don't have a single predicted match or mismatch between these 2 centromeres. So which one is correct? Let's go into this. What is wrong with the standard GP alignment? Let's assume that we have a sequence ancestor, and let's assume that in this ancestor there are 2 sequences, S and T, each of them generated from the ancestor by tandem deletion. And tandem deletion and tandem duplications are very common in centromeres or immunoglobulin loci. So if we start comparing these 2 sequences, each of them ancestor consisted of 5 units, and each of sequences S and T consists of 4 units. If we start comparing them, very nice alignment with just 2 mismatches, but completely wrong. If we wanted to find mutation, really mutations that happen, that would be completely wrong. This mutation did not happen. The correct alignment is this. So how do we find it? How do we find correct alignment? Well, what is kind of major problem with standard symbol by symbol alignment? Here I show correct matches between 2 sequences that I showed at the previous slide by colored dot. But there are too many spurious dots. There are too many matching symbols that are completely irrelevant for the alignment. They are not correct. So dynamic programming tried to reveal the correct colored matches in the sea of incorrect black matches. And in highly repetitive sequences, just doesn't work. That's why people actually are turning to k-mer by k-mer comparison, because in the case of k-mer by k-mer comparison, every k-mer by k-mer is more statistically significant, so there is more chance. And that's why these approaches like Minimap are so popular. And they're also fast. Fast is not the only reason for this in highly repetitive regions. They are also more accurate in highly repetitive regions. But even tools like Minimap fail in highly repetitive regions. For example, why? Because in centromere, most 100 MERs, and Minimap works on smaller k-mers than 100 MERs, most 100 MERs occur 1,000+ times. So just to figure out which of these 200 MERs really matching each other is hopeless. So what is wrong with the k-mer-based sequence alignment? That is what's wrong. This is a dot plot. It's basically every k-mer match here is every 100 MER match is shown by a diagonal line. But you don't see anything. It's kind of useless. And if you change k-mer size, it also doesn't change much. So deciding which of these pairs of k-mer is orthologous is hopeless. What should we do? The problem here is, the problem with alignment, that matches of frequent k-mers have the same contribution to the alignment score as the matches of rare k-mers or unique k-mers that are much more likely to be orthologous, because it's unlikely that unique k-mers just appear from a thin air. If they are unique and appear in two genomes, most likely they appear in ancestor somewhere. So we want to prioritize matches of rare, or let's talk about unique k-mer that are more likely to be evolutionary relevant. And our dot plot immediately makes much more sense. If instead of showing all k-mers as in standard dot plot, we will only show matches of unique k-mers that appear only once in one sequence and once in another. But it still won't work, because first, it's not clear how to select k. Then in different regions, there are different k's that are actually making sense. And that's why instead of unique k-mers, we are arguing that we should look for unique substrings of any length. If a substring is unique between two genomes, appears once in one genome and once in another, most likely the substring exists in ancestor, and that's why they are orthologous. And we can turn unique into rare, but for the sake of this talk, let's talk about unique. It's simple. And since the dot plot now makes sense, we can actually construct alignment by chaining this unique k-mers. Now our scoring approach now will change for every pair of string, depending on where these unique k-mers are. So a shared substring of two strings is unique if it appeared exactly once in each of these substrings, like this green one. A uni-alignment is an alignment that using this only unique substring as atomic unit for comparison. And immediately there are two questions. Are uni-alignment more biologically adequate than the standard dynamic programming alignment? And the second question, can we efficiently find unique substring and chain them, or small representative subset of them, and chain them so the uni-alignment is faster than Minimap, let alone dynamic programming alignment? So let's go to finding unique substring. Here I showed by black dot every starting position of unique substrings between these two sequences. Not that many, not as many as I showed at the previous slide, right? And I won't be actually using all of them. I will only use some of them, carefully selecting. And So that's the only unique substrings that I will be using, and then I will change them. That's what I'm going to show you, how to find this substring efficiently and how to efficiently change them so the algorithm is fast. Instead of two string S and T, we will talk about a single string, S concatenate with T. Okay? And we are looking for a unique substring, which means one of them appears once within red part, once within blue part, like this one. Right? But there is even shorter version, this one also unique. So how do we find? There will be many of them. How do we find them? And there are too many, so we want to work with a smaller set. So if we ask a question, if this substring is unique, well, we can definitely answer this question, but it will be very slow. And we need to answer this question for every starting position in the string, so it won't work. Instead, we will construct a sorted array of all suffixes of concatenate in our head, not in reality. We will just construct this array. It's a very large array. We cannot construct it in reality, right? And instead of searching for unique substring horizontally, we will search for unique substring vertically, because unique substring shown here in the green box appears in consecutive rows of this suffix array, right? And so we will call prefix of I is the longest common prefix between the ith row and the next row in this array suffixes. So in this case, prefix of I will have length 6. And we will record all lengths of all prefixes in the longest common prefix array, which, luckily for us, can be very efficiently constructed. Okay? Now, with this in hand, how do we answer the question if prefix is unique? For example, on the top, green prefix is unique. At the bottom, it's actually not unique. How do we quickly answer? We will just recruit, instead of a snail, we recruit a cheetah. In a single run through the suffix array, cheetah will tell us who are unique string, like this. How? Well, prefix of I is unique if it's formed by consecutive suffixes of different colors, right? One should be in red section, one should be in blue section, right? So they start from, one should start from red color, another should start from blue color. But that's not all. That's just a part of this condition. That's not sufficient. Another condition, prefix of I is unique if it doesn't appear in the previous row and if it doesn't appear in the next row, because otherwise it wouldn't be unique. So it doesn't appear in rows I-1 and I+2. And it already looks like a simple task for the cheetah. But remember, cheetah, we cannot afford storing this array. We only can afford generating this, right? So cheetah should make such decision without actually looking at what is in the suffix array. And it's not a problem, because cheetah should look just at 3 values: at prefix of I value, previous, and the next one. And if previous and the next one are smaller than the green one, it's definitely unique, because prefix of I doesn't appear before, doesn't appear later. So prefix of I should be longer than prefix of I-1 and I+1, which means that LCP, longest common prefix array of I, should be larger than maximum of previous prefixes and next prefix. And that's it. In this case, it is larger. In this case, it is smaller. And therefore, cheetah just goes and look for local maxima in this array. Local maximum, which means this value is larger than previous and the next. And that's how it finds. So that is clear, right? So in a single run, we will find all prefixes, but we will instead search solve a little bit more difficult problem, search for shortest unique substrings starting from a given position. And in this case, shortest unique substrings are here. I will explain later why we are interested in this SUS substring. How do we look for them? Well, we already basically solved this problem. Substring represents the shortest unique substring if it doesn't appear before and it doesn't appear after, in the previous row and in the next row. And we know the condition for this. SUS, length of shortest unique substring, should be larger than maximum of previous LCP and next LCP, larger but not too much larger, which means SUS should be equal to maximum plus 1. And that's sufficient for this being unique. So in this case, we look at 2, 6, and 3. Only 3 values we should look at. We take maximum of them, add 1, and that's the length of the shortest unique substring starting at a given position. So in a single run, the cheater not only finds all blue substring, but also all orange substring which are SUS. But that's not all. Because some SUS may be contained with another SUS. And we will generate uniseed. These are shortest unique substrings that are not contained, that do not contain other shortest unique substring. And in this case, we have only 6 such substrings. We map them to our original sequence. And we will now change them, not unlike Minimap. Okay, that's what is done. How to find this shortest unique? How to find this uniseed? We first generate all SUS. They are all given in the order appearing of the sequence. Then we sort them by their last position and select the shortest element starting, ending at the last position. One can see that that's how all uniseeds are generated. And now, finally, an answer to the question, why do we want to generate a small set of uniseeds and why uniseed? Because we will be using the sparse dynamic programming, which breaks the quadratic dynamic programming barrier of standard dynamic programming. So if we look at the finding longest increasing subsequence in the permutation, then in this, does it work? Maybe not. Oh. Then in this permutation, the longest increasing subsequence will be 1, 3, 5, 9, shown in red, right? And this, and this problem is basically equivalent to finding a longest common subsequence between permutation P and identity permutation. So it can be solved as the longest common subsequence. It can be solved by dynamic programming alignment, by just filling this dynamic programming table. On x-axis, we have permutation P. On y-axis, we have identity permutation. And these are matching symbols between 2 permutations. And it's solved in quadratic time in the length of the permutation. But there is something special about this dynamic programming table. The number of matching elements is small, much smaller than p squared. It's only p. And you may think that dynamic programming for sequence alignment was invented by Needleman-Wunsch, but that's not quite right. Much more sophisticated algorithm was actually invented in 1938 by Robinson, but was too complicated. So it was turned into beautiful algorithm by Schoenstatt in 1961, well before Needleman and Wunsch. And it's just a different way to solve the same problem and in nearly linear time, p logarithm p time. And it does something completely different. It doesn't build dynamic programming table, and I would say more beautiful. And that is dynamic, this is sparse dynamic programming. As soon as you have small number of entities to chain, you should use sparse dynamic programming rather than dynamic programming. Okay? So this is, yes. So we want to make the number of seeds small, so the next step becomes fast, thanks to sparse dynamic programming. And that's how the algorithm works. So we generate all uniseed, we project uniseed on the position of the sequence, and then we change them using sparse dynamic programming, and that results in running time that is practically linear in the number of uniseeds. And in reality, a number of uniseeds is 3 orders of magnitude smaller than the length of highly repetitive sequences like centromere. That's what makes the algorithm fast. Now, of course, we cannot afford generating this array. We don't have memory for this, but we don't need to, because everything I showed required only LCP array and suffix array. An LCP array and suffix array can be constructed very quickly thanks to genius contributions from 30 years ago. Now, a little bit further on Uni-alignment. Do I have time? Oh, yeah, I have plenty of time. Ah, good. Yeah. Now, you probably noticed that Uni-alignment doesn't have any mismatches, right? It's based only on matches, on matches of unique substring. Let's talk a little bit about this. Imagine 2 perfect sequences, 2 perfectly identical sequences. And let's introduce random substrings in the middle of these sequences. You will construct alignment, you will present alignment to unsuspected biologists, and unsuspected biologists will find a lot of mutation in this green segment, right? But these mutations are completely bogus. They do not represent, since a random string, they do not represent anything biologically relevant. However, how do you decide that this region of your local alignment makes sense, but this region doesn't make sense? There are some non-trivial studies allowing you to decide whether the entire local alignment or global alignment makes statistical sense. But there is no study telling you, well, your local alignment mainly makes sense, but this region, I'm not sure. Okay, so how do we address this problem? Is it spurious, statistically significant segment of the alignment problem? Anyway, when you look at uni-alignment, everything is formed by perfect matches, right? And then you look at insertion and deletion, and you have indel, insertion, followed by deletion. And its question arises, whether it's actually an alignment. There is some matches there, mismatches. What you do, you simply recursively apply uni-alignment to this area to decide whether it's spurious. Because for this small area, the set of uniseeds changed. It's now a different set of uniseeds for this small area. And you recursively apply uni-alignment, and that's what you get. You still don't have any mismatches. But if you have indel of size 1, and then insertion of size 1, followed by deletion of size 1, if you want, you can convert it into mismatch, right? Anyway, recursive uni-alignment, the path looks almost the same, but there are actually a lot of small changes. It's like decoration on this line. Result roughly in 30% increase this recursive procedure in the number of matching positions. And what are the parameters of the uni-alignment algorithm? There are no parameters. Now, of course, we need to benchmark it, right? How can we possibly benchmark? Nobody knows what are the ancestral centromeres, what are the ancestral. It's a very interesting question how the ancestral immunoglobulin loci look like, but nobody knows the answer. Of course, we do simulation. We know that centromeres and immunoglobulin, highly repetitive regions, evolve by duplications. So we simulate evolutions that include both mutations and duplications. and the accuracy of uni-alignment compared to standard alignment. Even with a small number of duplicated units, tandem deletion and tandem duplication, traditional alignment completely fails. Not to mention that even ad-lib becomes slow, but it's completely wrong. And if we bring minimap, it is better than ad-lib, but still quickly deteriorate with increasing of the number of tandem duplication. And when we look at time, that uni-alignment actually runs faster than ad-lib, and ad-lib kind of irrelevant here because it generates completely wrong alignment. And that's why it's fast, because it goes in a short band, and it's faster than minimap. What is interesting is that we decided, just as a matter, it was designed for this highly repetitive region as a matter of curiosity, but we decided to try it on regular regions. And it turned out that it worked very well on traditional non-repetitive regions. So for regions that are diverse by less than 10%, it performed roughly the same as alignment tool or minimap, and continues to be OK for lower regions, regions of similarity. What we learn? Extremely high rate of tandem deletions and tandem duplications in centromere, which gives us a hope that we can actually analyze recent evolution of humans based on centromeric analysis if we find accurate accurate alignment, and previously thought statements that there is highly increased single nucleotide mutation rate in this region is incorrect. Now, you may be wondering why these regions evolve so fast. One theory is, and why they evolved by such dramatic rearrangement of their structure. It's almost like they don't want to stay conserved. They want to change, like human immunoglobulin locus want to change all the time. Why is it happening? Imagine that a new virus comes in the human population. And this new virus has specific genes that is seemingly specific V gene that is the most well suited for fighting this particular virus. But it takes more than 2 weeks to develop viable antibody from this V gene, and person is dead after 2 weeks, right? So the simplest way to solve this problem is to increase the copy number of this gene by a factor of 5, because there are 5 more possibilities. You can kind of save a number of evolutionary iterations for developing antibody, and that gives you a range, much faster way to fight the virus, and then you possibly do not die during this fight. So this just accumulating in the population, large variation in the immunoglobulin loci allows human population to automatically develop variability with respect to fighting different threats, because the expression level immediately increases. And also, if you have a new copy of 2 genes, of immunity genes, 1 copy can find previous diseases, and another copy is free to evolve to find new diseases. Anyway, I'm coming to the end, just maybe 5 more minutes. Now, so when we look at the centromeric common ancestor, and we look at, let's say, your centromeric most recent ancestor on chromosome 10X, it may actually lived relatively recently, but if we look at the most common ancestor at centromere 12, it actually may live a long time ago. And at some point, the evolutionary signal will be lost. For example, if you're for something, and we see it, there are dramatically different variations in the level of similarity between different centromeres, maternal and paternal centromere, in the same individual. Okay? So if your region most centromeric, most recent common ancestor lived at the Neanderthal time, since centromere are so rapidly evolved, the signal is probably lost. So important thing is to figure out when we see something like this, it's a kind of extremely different, two centromeres are extremely different, it's mainly insertions and deletions. Is it real? Is it sporadic? Should we believe into this? Or is it real? It's like the same question as applied to classical alignment. Is classical alignment spurious, or should we trust it? But it's more complex. So what is statistical significance of uni-alignment? And this question actually goes back to the old problem that Stanislav Ulam raised, and he asked, what is the length of the longest increasing subsequence in a random permutation of order n? Once again, longest increasing subsequence question. And so this is two permutations, and I put dots at the position where they have the same element. So there are 8 dots in this diagram, and Lis of n will be a random variable representing the length of the longest increasing subsequence in this random permutation of order n. For example, in this case, it will be this longest increasing subsequence. And we are interested in this question of what is the length of longest increasing subsequence in a random permutation. And amazingly, this question was once again answered by people who studied this Robinson-Schoenstatt algorithm. And it was answered maybe 30, 40 years ago. And this is a famous Logan-Sharp-Vershik-Kerov theorem, very deep result based on Young tableau. And the length of longest increasing subsequence in random permutation is roughly 2 square roots from n. And then there was a follow-up work that distribution of this random variable is very tight, but this is an extremely sophisticated result, well above my pay grade, so I don't know how it was done. Anyway, so that's what we know. What it has to do with our problem of interest. Imagine a random dot plot, and we randomly just drop n points in the dot plot, uniformly at random. We can ask a similar question. Like we look at random variable that represents the number of points in the optimal northwest alignment path in this random dot plot. You see the similarity? It is somewhat similar to asking a question, what is the best alignment path in the random permutation dot plot? In the random permutation, dots are dropped on the grid. In this case, they're dropped just randomly. But it's known that this problem are kind of well related. So we assume that this variable is similar to the distribution of Lis of n, and then we can apply the Logan-Sharp-Vershik-Kerov theorem to this distribution informally. And looking at two centromere, we can actually construct a plot like this. We can construct an equivalent of dot plot for two centromeres that look like this. I won't go into the details. Now, if we constructed this dot plot for centromeres, and if this variable look like its value is similar to what we expect on average from random permutation, then we probably should declare this similarity as random. And I'm returning back to this plot from what I started. If you look at the dot plot here, it doesn't reveal any sequences, any kind of visible similarity, right? It's kind of and that tells us that maybe there is no signal left here. Maybe it's very distant, too distant centromere. Anyway, so using this analogy, and it is not a rigorous estimate, that's why it's an open problem for you to think about. I cannot solve it, it's very complicated. Yes. So in the spirit of Kerr-Logan-Shep theorem, we generate a rough estimate of statistical significance of Uni-alignment as reliability of AN as scorer divided by 2 square root from n's. 2 square root from n's, that's what Logan-Shep-Vershik-Karov theorem. If this value is close to 1, we probably deal with something that is sporadic. If this value is much larger than 1, we probably deal with something that is real. It's not randomly dropped point on the plane. Once again, it's not a rigorous estimate. It doesn't take into account variance. And when we look at this and apply this, it didn't seem to be working. When we have dot plots that make sense, reliability is high. When we have dot plot and extremely divergent Uni-alignment, reliability is low. So we're currently using this to decide whether comparison of this highly repetitive region is statistically reliable. For centromeres, it is clearly there are centromeres that are extremely divergent, and we don't believe this. For immunoglobulin loci, practically everything makes sense. And that's it. I think I'm even on time. Yeah. And this is joint work with a very talented student, Andrey Bzikadze.